Hello guys and girls, welcome to the computing workshop. I am the mad computer scientist and this is my workshop. So today we are going to discuss a topic that was or recently has been quite commonly discussed in various retro computing communities and like Facebook or Facebook groups or forums and so on. That is the topic of recapping. Whether you're in a vintage CRT monitor group or you're in a group for vintage computing enthusiasts or whatever, when you have something that doesn't work, there will always be like 10 people coming into a discussion thread telling you to recap. So instead of treating that like some sort of mythical buzzword, let's discuss what that is. So and I'll also show you how to do it. But recap means replacing capacitors, one or more capacitors. Now people tend to think that this is some sort of cure for all kinds of problems, whereas it's really not. It's like an analogy for doing a complete recap. Like some people recommend would be if like you had a loose wheel on your car and people told you that, oh, you better tear down the entire car and replace every single bolt within its construction, which would be completely useless. You would only need to replace the single one that causes your wobbling wheel or whatever, or you could actually find out that it wasn't actually the bolts, but it was the rim that was skewed or whatever. So like any other thing, recapping or replacing capacitors, let's not use the word recapping because that has become sort of like some sort of magical buzzword term. Let's just say replacement of a faulty component in general, which in this scenario happens to be a capacitor. But that being said, capacitors, especially electrolytic capacitors and so on, they go bad with age, right? So they go bad when they start leaking and so on, and then they fail. So replacing capacitors that have failed is, of course, a good idea. And there are some types of problems that can be, especially intermittent problems in a circuit, that can be traced back to faulty capacitors. That it's also a good idea to replace capacitors and to if they go bad, obviously, like any electronic component. Let's the idea is that I will discuss what a capacitor is, because also I think that instead of just replacing anonymous things on a circuit board, you should at least know somewhat of what the capacitor is, what it looks like, what it does, so on. And to help me illustrate this today, I have brought out this Dell motherboard. This is a socket 478B. It's a 478 socket motherboard from a Dell computer that has a bad capacitor, which we will replace. And I'll show you how to desolder and solder a through-hole capacitor, which is the most common repair that you would do yourself, is the through-hole ones. The surface-mounted capacitors, or SMDs, you can also replace those, but they require a bit different technique, but it's not really extremely hard either. Unlike what some people tell you online, it's not impossibly hard, even with just a soldering iron, to do that as well yourself. But normally the ones that will fail most commonly, and especially on these Dell motherboards, because these are notorious for this type of failure, is the lower quality electrolytic can-shaped capacitors like the ones you see here. And they will start leaking, and these are actually filled with a gel, an electrolytic gel that will start leaking, and it will mess up the circuit in general, or they will actually blow up, which can happen. These are also polarized, so they are plus and a minus. The electrolytic cans are polarized. If you turn them the wrong way, or if they short out in some way, they can also blow up. So and here we have one. I don't know if you can see, this is a cap that has started leaking. I took this from another, incidentally, another Dell motherboard, similar to this one. Dell had a real problem with this for a while by choosing bad quality capacitors. Now, before we start removing capacitor, let's discuss the capacitor in general and get a little feel for it. So the capacitor is a passive electronic component which is common to basically any circuit that you'll ever come across, such as this motherboard will have a bunch of capacitors on it. So what do they look like? Well, there is the can-shaped ones like this one, and this is an electrolytic capacitor. There are the ceramic capacitors like these. These are took this from on the bench somewhere. I got a ton of stuff here just lying around. These are disc-shaped ceramic capacitors. Then you have film capacitors. Normally looks like little tabs or blocks. Also legs on them. These have legs as well. This means that they are through-hole components. They go through holes on the board, and they're soldered on the back of the circuit board. Whereas there's also the surface mounts or SMD. Packaged SMD is surface mounted device, and unlike the through hole ones, these look like very tiny tabs, sort of, and they are really tiny. They come in a range of tininess, if you will, and they are mounted on pads on the surface, like the name implies, on the surface of the board. Now these pads are easy to burn out, or you can easily and then they're so tiny, so it's easy to drop them or have them aligned wrong when you put them on. So they're a bit more tricky to remove and solder back on. On the other hand, it's not impossible. Some people will tell you that you should stay away from it. I don't think so, and I would probably make another video at some point, I believe, to show you some techniques that you can use for surface mounts. But looking at the most common source of failure are these can-shaped electrolytic caps. They common on a lot of boards, also in a variety of power supply applications. Like I got no power supply here. This is a dusty old unit. Here we can see two large cans here. These are filter capacitors on the primary, the wall socket input end, the AC end of this. These are filter capacitors. They're large cans. So if those go bad, your power supply will have a bunch of, it will fail intermittently and so on. So it's a good idea to check capacitors for leakage and so on. Also do a visual inspection if you see one that's bad or is leaking or bulging, because these cans will also bulge. They will start bulging when they're going bad. You could remove them and replace them, and also removing to measure them. Remove them from the circuit. You can also get a meter that measures capacitance. And you can see that they are within specification. But remember, remove them from the circuit and then discharge them before measuring, to not mess up the measurement. And discharging a capacitor, do like this or something like this, and then you could take a wire or whatever. You put something metal between the positive and negative on like an electrolytic capacitor like this. You discharge it by connecting the terminals, so that way you can discharge the capacitor. Now on a high voltage capacitor like one found in a computer monitor or something like that, don't do that. Discharge that by running hooking a wire to one of the poles, and then through a sufficiently sized resistor, and then so that you slowly drain the capacitor, because otherwise you get a loud bang and a large flash, because a high voltage capacitor will normally also be one that stores also quite a lot of charge, and these can store charge for quite an amount of time. So you'd be surprised, it's a rather unpleasant surprise actually, when you're working on a computer monitor or something and you discover that it has a capacitor that actually still has charge in it, and you happen to touch the terminals together. That's not good. Yeah, so let's look at what a capacitor does. Now, just to get a feel for it, a basic feel for it. This is like electronics 101 here, but bear with me for a second. Now, the capacitor is a passive electronic component which main characteristic is that it stores a charge as an electric field. So quite like a battery, it will store a charge. So it will, while current is flowing into the capacitor, it will start charging, and once it reaches its capacitance level, which is the maximum amount of charge that it can store, it will stop current from flowing. It will not accept any more electrons flowing. What a capacitor does is, another characteristic is that it stops, it completely, once it's charged, it stops DC current, but it actually allows AC current and high frequency charges. So high frequency current going through it. So it's like in a DC circuit. This motherboard is a DC circuit. So in this circuit, that means direct current. So here we have, normally we want to have a current going through this, or several currents that are fixed. So it's like you want as smooth voltage as possible. So you want it, basically, preferably would be to have it like a solid 5 volts or a solid 3 volts of charge or of potential in the circuit. Whereas in alternating current, or AC, which is the one you have in your wall socket, for instance, you have charge goes like a sinusoidal curve, like a wave. It's a waveform, so it goes from a positive potential or charge to a negative one, and then back to a positive, and so on. So you have like plus 12 volts, and then so if you would have an AC wave in 12 volts, you will have like plus 12, minus 12, plus 12, so on and so forth. It will alternate between positive and negative voltages. We won't go into that now because it's unnecessary for this, but just bear in mind that these will block DC current from flowing. So if you were to put a capacitor in between, like something like like a ship or something, and then you have current flowing in, then after a very short while the current will stop flowing altogether. The capacitor will block this. It's actually an insulator, it has a very high impedance, so it will stop current from flowing. It will basically stop all DC current. And the way it's made is that it has two plates within it, which holds, like a battery, they hold a potential between them. So it charges up a positive potential on one side, one plate, and a negative on the other. So this creates a voltage. So there becomes a voltage across the capacitor. So it becomes basically just like a battery. You could actually test this for yourself. If you connect a battery and charge up a capacitor, and then you put the capacitor instead in series with something like an LED light or something, then the capacitor will, while discharging across the LED, will actually drive the LED for a brief period of time before it discharges and goes back to its neutral state, in which case it will need to be charged again. So it's sort of like a battery, only that it has a very short, it will release its energy very quickly. So what are the potential uses of a capacitor? Well, there are some potential uses of the capacitor. I actually drew some pictures here while I was preparing to record this. One of the most common ones, like what are they used for on a circuit board? Well, the first one is in power supplies and in power regulation. So in a DC, we will not discuss the use of capacitors in AC circuits because AC circuits is a different thing altogether. But in a DC circuit, you have, if you have a power supply, like, I don't know, hopefully you can see the picture. If you have a power supply, like the one pictured on top, you have this AC current that will go from this, the 0 points, will go from positive peak to negative peak and then back up again and so on and so forth. Now if you do regulation, which you do in a power supply, for a computer for instance, you want to have this DC voltage I was talking about. You want to strip out one of these, so you want to have only like plus 5 volts or something. And that way you take away this by using a diode bridge or something like that. You take away the, in this case, the negative part. So you get only the positive waves, or the positive part of the wave. But this, as you can see, is very uneven. So now you will have very uneven voltage because it will rise and then it will reach peak and then will drop again. So if you put a capacitor, however, into this circuit, you will have a rise, and while it is rising, the capacitor will charge. Now, by selecting the correct capacitor, you could make it so that when the voltage from the supply is dropping, the capacitor will actually start discharging into the circuit, keeping this much more even, and then while this is then rising again, it will start refilling the capacitor, and this cycle will repeat, so you will get more like an even voltage in the circuit. So this is a very common use of capacitors in circuits, and of course in power supplies, especially in switched power supplies. Another common use of the capacitor, I do another picture here which I hope that you can see, is the decoupling capacitor. Let me adjust, maybe you can see it like this. Okay, so this is the decoupling capacitor use. If you have a chip here, this is the most common use in basically any digital circuit. So you have the excuse my bad drawing skills, by the way. I was just doing these drawings in like 5 minutes before, but also from the top of my head. So actually this is probably not the best way to explain this, but if you have a chip or something on here, you could have a noise coming from the power supply. So if this is voltage in coming from power supply, and this is the VCC, this is voltage in on the input pin on the circuit, the IC or the chip on the board, and this is ground pin. So if there's noise on this, like if this VCC, this noise can actually interfere with this very delicate chip. So you want to get away this noise, and this noise is actually high frequency, whereas the 5 volt DC that you want is something more like this. So you want this solid, nice 5 volt signal, whereas you get something that looks like this, which is filled with noise, right? But remember what I said, that DC cannot pass a capacitor, but high frequency or alternating currents can, which means that if you do add capacitors here, the noise part of this, the alternation, they will take the path of least resistance through these capacitors with carefully selected values, and they will go into ground. They will go down to, they will be tied to ground. So you will get a much cleaner signal here. And this type of filtering and decoupling is probably the most common use of this on a something in a computer, to decouple it from the noise. Also, if you have, this is also known as, also this can act as a bypass in if there is a voltage drop, which is actually quite common in power supplies, there's voltage drops. Something is increasing its current draw, and then all of a sudden there's a voltage drop in the power supply. So the voltage, then these capacitors can also start discharging, providing the necessary voltage all the time to this logic chip here. And also there's this thing with the transient loads. Like if you have a logic chip which is controlled by a pin, you want a logic signal which is either a 1 and a 0, right? And if you have these connected to the same power line, or connected in a circuit with another chip, then the different circuits can affect each other, and you don't want that. So because then you could get this, like when this chip goes into like this, you can see here on the picture, when this bottom one goes into like a rise, a signal, then this rise will actually cause a ripple and a disturbance on the second circuit, which will cause it to read a 1 here, while you actually intended for it to be 0, which will often also happen when it drops. So when the circuit then goes into 0, one of them, then that could cause a ripple that will also read as a 1 on a different circuit, and you don't want that. But by adding a capacitors in parallel with these, you can avoid this, because you're decoupling them from each other, because these kind of ripples will be swallowed up by the capacitor. That's also a common use of the capacitors. So those are like the most common ones, like bypassing, power, smoothing out power delivery, bypassing, and also to act as a voltage backup, a backup supply if there is voltage drop on a power supply. So that is normally what the uses are on a DC circuit. For instance, on the buses here, you can see there are some capacitors here. I would suspect that these are actually for when signals are carried on the bus. You want this to be as even as possible. You don't want any transient loads that will affect the signals going across the bus. Also around the CPU, there's a lot of them. So when you find one that is bad, either you find a surface mount which has burnt out and left like a black spot on the board, or you find one of these electrolytic, the can-shaped ones, or a ceramic one that has actually cracked open or burnt out or something. There's also tantalum type, which are drop-shaped ones. Normally these are quite common in like early IBM, like 5150, 5160 XT, so on and so forth. But if you find one that is bad, then, or you suspect that one is bad because you have intermittent failures on something that can be traced back to one of the chips or the part of the circuit that should be filtered, which appears to not be filtered, like you have an input which is reading 2 inputs at once or something. There's some disturbance on the signal, and you figure out that there's some capacitor that is wrong. That is so how do you figure out which one to replace it with? Well, it's actually says so on the capacitor. Normally this one says, for instance, 4.7 microfarads. That is the amount of charge that it can store between its plates. So that's measured in farads. This is the capacitance. So this is 4.7 microfarads, and it says 100 volts on it, and that is its voltage, the maximum amount of DC voltage that it can withstand. And then it says -40 to +105 degrees Celsius, and this is the operating temperature. So look for a capacitor that has the same values. You could have a higher voltage rating, that's not a problem, than the one that is in there. but you should make sure to have the same capacitance. Unless you know exactly what you're doing, because in some cases they are just used to block DC current from one part of a circuit to another, and in that case you could just pick anything that is sufficient to block it fast enough. Like around these ceramics it says 101 on it, and this means that these are 100 picofarads, because these have different markings. These are, the first two digits are 10, and then it's the multiplier. So in this case it's 10 times 10, which is 100 picofarads on these ceramic ones. So that is basically it. Now we have discussed the capacitor, we have actually gotten a feel for what it is, and it's just like any other component. Don't replace it until you actually investigate what is wrong, and don't just recap everything, because that's just a useless amount of work. Unless they all are looking sad and old, and then yeah, go ahead. And if you feel like recapping all of them, then, or replacing all of the capacitors in this sort of full recap that people are telling you to do, then why not? You could do that as well, but it's some work, especially on a large motherboard like this. And also be mindful of the high voltage ones, like I said, in like monitors or power supplies and stuff like that, because those things you don't want to touch the term. They can hold a charge for a long time, and if you do something like this and you happen to pass the current through yourself when shorting out the terminals, that's going to be bad. So it's not going to, probably not going to kill you, but it's not going to be nice either. So now I will cut to the clips I made where I actually replace one of these bad capacitors. You can also see how that is done using just using a normal soldering equipment, which of course you need to own before replacing anything, even through-hole components like these. Alright, so let's see if we can desolder this thing. We will let's first find it. So we first got to find the one we want to remove. It's right there. Piece of cake. And normally it comes out easier if you push. Got the iron, by the way. Just gonna do this on a sponge for a while. This is a temperature controlled soldering station that this iron is connected to, and I got it set to 406 degrees Celsius, which should be okay. It's a bit, could go 420, but let's just do 406 for now. And the one we want to remove, let's just double check so we find the right one. And of course I'm not using some sort of solder surface or whatever, because this is my workbench, so I don't care. Normally it helps if you heat it up and you put some fresh solder on it, because it helps to get the old solder to, yeah, let's feed some on there. It helps get the old solder out. It draws the old solder out, as you will see. We'll feed some new solder on there. Oh, really nice. Now, don't be afraid of this, because if you got a decent iron and a decent, the correct temperature, this will be quite simple as long as it's through-hole components. So you should really not be afraid of doing this yourself, because it's really simple. So let's first try with the plunger. This is very cheap. This is the cheaper option, using the plunger. So you melt the solder, and when the solder is melted you suck it away from the board, right? So let's do that. Let's melt all of the solder and suck it away from the board, and it's a clean break. Awesome. Okay, it's loose now. Good. Wipe the tip on the sponge. So that was the plunger. Now let's see what happens if we try with the soldering wick. Give me a second. This is actually better if we normally I do this. Let's see what I mean. 1 second. Give me a second. Let's see if I can find some good tool to use, like this one, to get a fresh piece of wick that we can use. Maybe. Let's see. Here we go. So we got a fresh piece of wick right here. Whoops. Oh yeah, this is luckily but rather horribly actually, my motor skills are horrible, which is why I'm a software engineer, electronics hobbyist, whatever, and not a fine handicrafts guy, because I don't have the motor skills to work with that. Okay, so let's melt it and then put the wick to it, and it will suck up the solder. You could also push it in there really good like this, and it should suck up the solder. Yeah, and it does. It actually sucks up the solder from this, and it does. So this takes a bit longer time to clean up using the wick, but it works. The wick actually does work, and it's actually a bit easier using the wick, because using the wick will draw out some of the excess solder because it's fluxed. So you can either push the wick on there like this, or you can first melt the solder and you can run the wick across like this. It should suck up all of the solder as long as you got enough heat in the iron. This of course takes a bit of extra additional heat on it to get it out. So now, so as we can see, after some cleanup, fixing with the wick, thing is finally out. Now we have the holes to put new capacitor in, and here it is, the one we removed. Let's see if we can get it to focus on it. Maybe camera doesn't want to pick it up. I guess that's a bit too close to the camera. Focus is not really working, but yeah, you can see that it's popped and it's leaking a lot on top, and it's bulging, and this one is really bad. So let's get new one, similarly rated one, and the way we do this now is we plug it into the same hole. Sorry, this is not the right one. Actually, I don't know what I'm looking at here. Let's try a different one, like this one, which is actually working. Let's plug this one in. The other one had a leg that was broken and cut, so that's not gonna work. Let me just adjust the soldering station to some more comfortable temperature. I had it on like 450 for sucking up the solder that got stuck in the through holes. So let's see where the hell was the one that I removed. This is one of the harder parts, is actually figuring out. You actually lose. Oh, there it is. Okay, so looking at this, you can see that there is a. Now you can't actually. Maybe you can if we do this. Camera mount isn't exactly the best. See if we can. There is a minus. There's a white. There's a circle here where the capacitor was seated, and there's a white one which indicates negative. So we will look at our capacitor and we will see that there's a stripe there. So we'll put the stripe, the white side of the circle, where the printed circle on the board. We will push it in like so. Here it is. So our new one, a replacement capacitor, is in. And now what we have to do is solder it in place. So we turn the board over. We can twist one of the legs a bit. We bend it a bit so it doesn't fall out. Normally you could have a clamp or something that would help you. And now we'll just do a nice clean solder this thing wherever I put it, which is right there. Let me just grab a smaller. Let's see if I have a thinner. I'll just check to see if I have a thinner solder wire, because that helps, I think. And some you can have different thickness. So if you're wondering what I'm doing, by the way, I'm actually rummaging through a box of stuff. See if I have some. Okay, this is some really thin wire. This is extremely thin solder wire, but why not? Let's take this one. This is a very thin wire. Let's cut this. As you can see, this is extremely thin wire. Maybe it's a little too thin, but on the other hand, I found this wire now, so let's use it. And the way we solder something is put heat onto the leg and onto the pad. The pad is the circle or the hole itself, which is conductive, the metal ring where the, so you put your iron there and touching the leg as well, and then you gently push the solder wire onto the tip of the iron and the leg so that it forms a nice, and as you're pulling it away from it, you pull it upwards so it forms a nice, I will show you. So you do this, you keep feeding it and you pull it, keep feeding some more. This is a really thin solder wire, by the way. Keep going, keep going, keep going. That's a very thin wire, and that's a nice joint. And there you have it. And we can do the same on the other leg. So we do this, we start heating up the, okay, this wire is ridiculously thin, but it works sort of, but we need to feed a lot of wire to actually get enough solder to make the joint. But Nonetheless, let's heat up the leg and the pad or the metal ring, and then feed the solder like this onto your iron and to the leg. Keep feeding it and pull it out. Maybe a little more. There you go. That's a nice joint, that one as well. Wipe off the tip of the soldering iron, so you don't want any residue on it or oxidization. So wipe it off on the wet sponge that you hopefully prepared beforehand. So now it should be in place. Let's take this one away, and those are some quite decent joints right there, and there it is. So new replacement cap. So not very hard to do this. So our checklist is look at what looks bad, especially take care of looking for leaking electrolytics. Now if they are leaking, then you should replace them. If they are bulging, whatever, and then if you have intermittent weirdness in a circuit, look around a circuit diagram if you can find one for capacitors used in filtering or in decoupling, and maybe desolder those and measure them, and if you can measure them using a multimeter set to resistance, measure resistance in ohms, and that can at least tell you if it's completely broken or not, because then it should have should go very quickly up to infinite resistance on DC load, which your multimeter will be, unless if you wanna, you can also get a capacitance meter and measure the exact capacitance. So now that's basically it for now, and you can see that we have soldered this new capacitor on, and it wasn't really that hard. So it's not difficult. Just make sure you have a soldering iron. You may want to have a wick, solder wick, or a plunger, or both, and as of course the soldering iron itself and a set of pincers, and you should be good to go, at least for through-hole components like these electrolytics. Now surface mounted devices, you may want to use the hot air station or something like that, because it makes it a lot easier. But don't be afraid to switch out bad capacitors, but also don't fall into the trap of like thinking that recapping, if you call it that, is a solution to everything, because it's not. But if it's evidently is bad, then you should replace the capacitor, and as you have seen, that's not very hard to do, and it's also, as long as you put it the right way, like an electrolytic capacitor, like I said before, is polarized, so you want to put the positive side and the negative side in the correct way, and the negative side is normally marked by a stripe or a minus sign or something like that. So make sure you put it in the right way, otherwise it's not going to end well. So apart from that, it's not really that hard. You just desolder, pull out, put in a new one, solder it in. But like I said, everything in moderation. Like don't go recapping everything just because normally that doesn't help. But if there is an intermittent issue, that could be traced to filtering capacitors, or to maybe in a power supply you may have a lot of voltage drop, or you may have a ripple, current rippling. You may oh, I'm sorry. And I will not cut that out because I don't care. But yeah, so that's it for today, and I hope you recap something. Next session will probably be looking at something completely different. I'm thinking that I haven't programmed in a while on a vintage computer, or in a while, it's like in a month, but anyway, I probably should get back to doing something like that. So maybe we'll look at Pascal or something. Pascal is always fun. So yeah, thanks for watching, and keep safe.